Good day, everyone. My name is Ali Mahmood, and we will be presenting our issued paper titled Design, Fabrication, and Performance Evaluation of a Hybrid Linear Generator Reciprocating Air Compressor using a magnetic coupled piston, or in a short way, as we like to call it, a hybrid compressor. Our presentation today will begin with a restatement of our thesis, which kinds of go over the importance of industrial use. We will give a brief background of how industries could benefit from hybrid compressor. Following that, we will discuss the design fabrication stage and end with the interpretation of the results. In our issued paper, we argued that on a yearly basis, worldwide, industries consume nearly half of the total power generated. This number keeps on rising due to the global economic growth. It is said that motors are the heartbeat of the industry. These motors are highly responsible for such titanic consumptions. They are used to run conveyors, refrigeration, air conditioning system, and other automotive system. Half of the total energy demand for the industries is used primarily for air compression. With such consumption, there is a dire need of sustainable design to lower the carbon footprint and for energy efficient air compression system. Zachary Shan, who is an author of Clean Technica in 2013, argued that 90% of the industrial motor often run at full speed, and some mechanical systems are used to regulate their output. So this got us into thinking that regulating motors in such a way does not make it efficient because the input power is not regulated. The solution to that is the use of variable speed drives, now commonly used in the industries. With such drives combined with the proper design, the efficiency of motor has significantly increased as the motor only uses the amount of power needed for the task at hand. So we decided of an innovative way to improve the efficiency of the reciprocating air compressor by designing a hybrid air compressor. This is a fusion of two technologies, linear electrical generator and reciprocating compressor. The idea of our prototype is to design a reciprocating air compressor whose piston is the translator of the linear generator. Under operation, the compressor functions as a conventional reciprocating air compressor, but generates electrical power at the same time without significantly compromising its compressive work. Thus, the overall efficiency of the compressor is expected to significantly increase because of the extra electrical power output. When we think of the millions of reciprocating compressors out there, like in refrigeration system, pumping system, manufacturing industries, which are working with efficiencies lower than 60%, so there's a need to improve the performance of such system. Manufacturing plants, oil refineries, workshops, and the likes, they can benefit from this innovation with the possibility of increasing the overall efficiency of their air compressor. In the process, the important thing is that the cost of running the compressor is significantly reduced. In our design and fabrication stage, here there is a process flow diagram showcasing the step-by-step process of how we design the system, followed by fabricating it and performing tests or evaluations to gather the data and analyze it. For our first, we started with the piston, where piston is considered to be the heart of an internal combustion engine. just like motors, which are considered to be the heart of industry. So the role of piston is to translate mechanical energy developed from the crankshaft to the air in the cylinder. The piston is connected to a connecting rod, which in turn is also directly connected to the crankshaft. In our piston design, we initially use a block of high steel material as the piston head. We use the lathe machine to reform the structure. However, we met with a certain disaster. Like during the operation, we found out that the lathe machine was not able to handle the toughness of high steel. This resulted in the cutting tool to be broke down. Good thing we replaced the block of steel with aluminum. Our team performed the same operation as we did in the steel block, like using the lathe machine for facing the end part of the piston head, cutting it to be in specific dimension, boring to attach the piston rod, straight turning for adjusting the diameter, grooving for the placement of neodymium magnets, and finally chamfering for the purpose of attaching the piston rod. The important aspect about the design of the piston is that in the grooved area, we use super glue to attach the neodymium magnets because our piston will act kind of like a linear generator. Why did we attach it? Because following Faraday's laws, when you equip magnets to a piston and it moves in a cylinder covered with magnetic coils, voltage would be generated. And this voltage is the result of the change in the magnetic field of the coil. Next, in the design of the connecting rod, we use a bar of metal, and we reformed it by changing the shape using a milling machine and drill press. Two of its ends were drilled with a drill press, and we attached ball bearings. The unique part in the design of our connecting rod is how we structure the thickness of the middle part. As you can see in here, our team used a milling machine to reduce the thickness so that the connecting rod does not hit the inside surface of the cylinder and to give allowance during the compressive work. Next, for the flywheel, everyone knows that flywheel converts reciprocating motion or linear motion into rotating motion. The flywheel in our design was salvaged, luckily, and also welded. After welding, it has been furnished and repainted for aesthetic purposes. Holes were drilled to connect it to the shaft of the motor. We used threading tab so that the holes underwent threading operation to hold the shaft lock for it to be stable. Our cylinder, we ordered it and specifically manufactured it from a manufacturing company. Due to the manufacturer standards, it was not available in our specific dimensions. However, adjustments were made where the cylinder underwent straight turning operation for the placement of coils and steel rings. Now, the shaft lock key was made from a block of carbon steel and aluminum. Its main purpose is to hold the flywheel and to not move it either inward or outward during the operation of the prototype. For the galvanized iron sheet, plasma cutter was used to cut it into our designated rings. We use large and small rings ranging in different sizes of outside and inside diameter with 320 rings of outside diameter and 212 rings of inside diameter. For the laser cutter, we use it to cut acrylic sheet into our desired designs, which would be mounted onto the acrylic sheet with two holes where there will be an inlet and outlet holes for the valves. The parts being made serve as the enclosure body of the cylinder. Threading has been made to each different hole in the prototype to hold the materials together. Silicone sealant were used to seal the gap created in between the different layers of the acrylic sheet. In the process of thread making, we use lubricants like oil for easier process. We also use like C-clamp to hold the different layers of the acrylic sheet, which will be used for the cover together. So earlier in the slide, we attach permanent magnets on the groove area of the piston. The type of magnets we used was neodymium magnets, as it is the strongest type of magnets available commercially and is widely used in many modern products. Another good part about it is that it is available at a low cost and at high magnetic field strength. Since the linear generator was designed with 9 slots, 2 sets of toroidal rings were made using a winding machine. It was made with 24 American wire gauge and 28 American wire gauge wires with 500 turns in total. The leftover wires were soldered together to save cost, and it was mounted to the acrylic cylinder with galvanized iron sheet. In order to measure the efficiency of the air compressor, linear generator, hybrid linear generator reciprocating air compressor, and to establish the load characteristics of the hybrid system, 4 cases were conducted. There are varying air compressor speed, hybrid generator at constant speed, linear generator at constant speed, hybrid generator at 100% load, and varying speed. The test was conducted in a room with ambient temperature of 21 degrees Celsius and an intake pressure of 1 atmospheric pressure. The test was designed to measure the efficiency of the air compressor when the linear generator has no load. The RPM of the motor is varied to determine the work of compression. In our first case, 5 trials were performed, increasing the speed of the compressor from 300 to 140 revolutions per minute. As you can see from these 2 figures, the speed of the compressor varies the work of compression, efficiency, and power input. So we know that an increase in the speed increases the work of compression as well as the input power. The optimum operating power of the compressor for this test was measured to be 300 to 350 revolutions per minute. At this speed, we recorded a maximum efficiency of 24%. However, due to the misalignment in the connecting rod, we could not run at such speed due to excessive vibration. At case 2, we tested the linear generator at constant speed, but varying loads. The intake and exit valves of the compressor were left fully open so that to ensure that the compressor is not doing any compressive work. At a constant speed of 360 RPM, 7 light bulbs with maximum power of 29 watts were used as loads. To establish the load curve of the linear generator, the load was varied from no load to full load, incrementing 25% at each trial. Then, using a digital multimeter and clamp meter, the input-output voltage currents were measured to compute the power and linear generator efficiency. So at a constant speed of 360 revolutions per minute, under no load condition, the output power and efficiency is 0. It is not recommended to run a generator at no load for a long time. For each trial, we increased the load by 25%. At 25%, we found it to be not cost effective. At 50%, the generator begins to reach, and the efficiency more than doubles from that of the 25%. When the load increases to 75%, the input power is the lowest of the trials, which is a good thing. And the generator have reached its maximum peak point, and its efficiency is 3 times that of the previous trial, which is the 50%. 100% would be a downfall, as it would create an increase in input power with small increase in efficiency. Therefore, it is best to run the linear generator at 75% load for less loss and a desirable efficiency. For case 3, the compressor and linear generator was kept constant, while the load was varied from no load to full load. This was performed to provide a basis of comparison between case 1 and case 2, determining at which load the hybrid system works best at constant speed. As the load increases from no load to full load, the output power of the linear generator also increased. The lowest efficiency was at no load condition. So it is not recommended to run the system at no load, since the motor will draw the highest current and it will heat up. From 25% to 75% load, the input power decreases, while the combined output of the hybrid system significantly increases. So for our last case, in order to establish the relationship of the hybrid system under varying speed and 100% load, the 7 light bulbs were connected to the system as a fixed load and the speed was varied. Based on the output curves, lower speed favors the linear generator, but it is a drawback to the compressor. So the overall of the efficiency of the system was also low at roughly 9%. With a combined output of 207 watts, reaching at a speed of 300 revolutions per minute, the efficiency reached a highest record of 22%. At this speed, the motor draws as much power as seen as the curve above. So there will always be a compromise between the outputs of the compressor and linear generator. However, they should be kept as low as possible. So here, this shows the operation of the hybrid compressor running at full load from an isometric view to a top view. So the primary aim of this research paper was to evaluate the concept of cogeneration through the hybridization of a reciprocating compressor and a tabular linear generator, which has not been performed thus far. 4 tests were performed using 4 different test conditions. It was found out that the work compression varies with the speed of the compressor. As the speed increases, the work increases, as well as the input power. The optimum operating speed of the compressor was determined to be between 300 to 350 RPM with a maximum efficiency of 24%. Varying the load of the linear generator affected its performance. By varying it, we reached at an optimum load of 75%. At this load, the efficiency was 3 times that of the 50% condition. The hybrid system also works best at this condition. At full load and a motor speed of 320 revolutions per minute, both the compressor and the linear generator has an output power of 207 watts with an efficiency of 22%. At this speed, the motor draws in more power. Hence, there will always be a compromise between the output of the compressor and linear generator, which should be minimized for better results. In our recommendation, the main input power source of the prototype was selected to be an electric motor, which was not manufactured to be controlled with varying rotating speed. Without reaching its designated rotational speed, one of the capacitors with lesser capacity would be heated up and produce smoke. There was even a loud spark. its designated rotational speed is actually 1,730 revolutions per minute, but our prototype was not able to handle that speed. Also, due to the incapability of varying speed by itself, a commercial and speed converter was used. This allowed changes in rotational speed, but it was not able to produce the stable rotational speed. Despite using one of the strongest magnets, we were unable to find a ring-shaped magnet with application size to the piston. Instead, we used smaller circular magnets with diameter of 9 millimeter. And the drawback was that there was an air gap in between every magnet, which were not conductive for maximizing their magnetic efficiency. Lastly, the most important part is that the prototype should be highly stable. When we mounted the prototype onto the main wood base, there was a strong vibration which hindered reaching its peak condition. It was mounted to the table with a C-clamp to reduce vibration. High vibration might cause severe damage to the prototype. Vibration can also be reduced with proper alignment of the shaft, flywheel, connecting rod, and the compressor. So that's all for my presentation. Thank you very much for listening.